but I was hoping I could put up some more videos of the whole process. So there's this process that you guys need to be able to do in this class. And it's basically starting with Gauss's law, that's the ideal scenario, or Coulomb's law, which is much more difficult. You're supposed to be able to derive the formula for the electric field around an object. And specifically what I'm shooting for is flat objects. So ideally it's an infinitely large plane, but that really just means you're maybe a factor of 10 closer to the plane than you are to its edge. If you keep it at least a factor of 10, but preferably a factor of 100, then the results turn out pretty good, okay, for treating it like it's an infinite plane. Also for a cylindrical object, whether it be a cylindrical wire that has almost no physical size, or a physical wire that actually has a robust diameter of maybe even inches, or a coaxial system, which is again cylindrical. So you'd have like a thick wire like that, and then outside of that a thick cylindrical shell. Those are things where you need to be able to use Gauss's law or Coulomb's law. Obviously Gauss's law is a better scenario with these symmetries to calculate the electric field. And then the other one is again spheres and spheres inside of spheres and that sort of thing. Once you have that electric field, then you're supposed to be able to use the change in voltage is equal to the negative integral of E dot dl to compute the voltage difference between two particular parts of those things. So if you, for instance, take two flat plates and put them fairly close to each other, then you want to calculate the electric field, the voltage difference between one plate and the other. And if it's a coaxial cable, then you want to calculate the capacitance between the inner cylinder edge and the outer cylinder inner edge. And if it's a sphere, you want to do the same thing between the inner sphere's outer surface and the outer sphere's inner surface. Again, calculating those voltages. Once those voltages are done, then you can use C equals Q over V to calculate the capacitance. So it's like a three-step process. And in fact, there's going to be an exact analogy when we get into magnetism, where we're going to use, instead of Gauss's law or Coulomb's law, we'll use Ampere's law or the law of Biot-Savart to calculate a magnetic field. Then we'll use the definition of magnetic flux to calculate the flux. And then we'll use the fact that the inductance is the flux divided by the current to calculate the inductance instead of capacitance. So these are three major terms: resistance, inductance, and capacitance are three major terms that are of importance in electricity and magnetism with regards to circuits and stuff of that sort. So that's really sort of the main goals, or part of the main goals, of the electricity and magnetism portion of this course, which, this course is also going to cover some thermodynamics as well as some quantum mechanics. So I'm putting more videos like that online. I've done them 1,000 times. There's already a ton of videos up there, so do check them out. Just go to my YouTube channel and do a search of my YouTube channel for PA or for 242, and you'll find all the videos that I've made that were specifically for 242. Or then you can do searches for Gauss's law or capacitance or any of those words, voltage, any of that stuff, and you'll find other videos that you can watch as well. I just want to express that I can't always work every example in the book or even make one exactly like every example, but I want you to know, sort of the whole chapter is what you're responsible for. So use that extra time to figure out the stuff that I don't get to cover that well. So again, does anyone have any questions before we get started on the material? Okay, so I've shown you basically how to do this, the calculating the voltage and stuff, but there's other things that we have to deal with regards to capacitance. And for instance, let me go ahead and write this down today. This is PHY 242, and we're looking at 13122. And let me turn on my document cam. Actually, before I do that, so we've told you that this capacitance is sort of something that allows us to store energy, and it does. And we're going to calculate, how much energy it stores, and we can even solve differential equations for the circuits that are set up that allow us to figure out, how the charge of the capacitance changes as you're charging it up or as you're discharging it, how the current leaving the capacitor changes as you're charging it up or discharging it, and even how the voltage changes as you're charging it up or discharging it. But we also need to know how it behaves in a circuit, because in a circuit, we're going to have capacitances and they do very specific things. They can be used for low pass filters or high pass filters. Actually, I always forget which one's which until I work out the details. So that's why I'm covering my bases and saying both high pass and low pass filters. But the high pass filter is also called a differentiating circuit, and the low pass filter is also called an integrating circuit, which is kind of neat, but they literally mean they can do mathematics electronically. So if you take, for instance, a signal of voltage or current that represents some mathematical function, in other words, the voltage is a function of time or something like that, and you apply it to an integrating circuit, you will get out of that integrating circuit the integral of it. And if you apply it to a differentiating circuit, it will literally spit out the numerical results of differentiating that. So it's a kind of cool stuff. I like it. I think it's very interesting. And I like electronics in general. So to do that, so I'm going to remind you of some facts, and I'm going to try to walk you through how a capacitor behaves when you connect it to a battery. And we're going to derive some results. So let me go ahead and turn on my document cam. So first off, I want you to see what happens. Let's imagine we connect a battery like that of voltage V, and let's make sure it looks not too bad. A battery of voltage V, and we're going to connect it to a capacitance of capacitance C. Okay. Now, what is going to happen? As you know, this long line represents the positive side of the battery, and the short line represents the negative side. So what's going to start happening is this battery is going to, we like to picture it as the battery is like a pump pushing positive charges out. And it's not really exactly doing that. I mean, on the conceptual level, it's fine to think about it that way, but really at this level of physics, we need to know that it's not actually doing that. It's more or less establishing an electric field that points along and sticks to this wire all the way around. And because of that electric field going this way, that would tend to compel positive charges to flow around this direction, because wires are made of conductors, and conductors have charges that are free to move around. So what will happen is it'll compel a buttload of positive charges to run this way, and they'll start to stack up on this plate over here. And as they stack up on that plate over there, that plate over there is going to compel a lot of negative charges to come towards it and a lot of positive charges to run away from it, until that face ends up becoming covered with negative charges. And in fact, the two charges will be exactly equal in magnitude, but opposite in sign. Okay. And that Q will be given by C equals Q over V, or, you know, it basically that expression. Okay, that's how it works. If I were to cut the circuit and stick another one in there, then all the charges from this guy would cause the other one to become positive, and then the other one on the other side of that would compel that one to become negative. So even if you put several of them in series, you're still going to get sort of the same scenario. So with that in mind and that description of how it's going on, let's consider, for instance, a case where we have two capacitors in parallel. So I'm going to have a battery again, V, and I'm going to have a capacitance. I don't know why I just drew a curve on that all of a sudden. I think I was thinking of writing the letter C. So we'll call that C1. And then in parallel with that, and this is parallel, by the way, this is something you may or may not have really heard of yet, but when you think about the charges leaving a battery, and you see that at some point in their journey, they get to choose one path or another, then those two paths are in parallel. So right here, when the charge gets to this particular spot, it has the ability to, in some sense, choose to go this way or choose to go that way. Since it had a choice, we call that parallel. So that's what it means to have two capacitors in parallel. And in fact, the total charge that comes out will be Q, and some fraction of it will go this way, and that'll be positive Q1. And some fraction of it will choose to go this way, and that'll be positive Q2. Okay. But since the total is Q, we know that Q is equal to Q1 plus Q2. Now, what we also know is that since they're in parallel, they're also at the same voltage. That's one of the things you've been learning from lab, is that circuits in parallel, or you will learn in lab, circuits in parallel actually create circuits that are like voltage. And let me explain how you can think about that. Remember, I told you one way we can picture this is if it's a three-dimensional model. And in fact, we're looking at it from above, so we can't see the third dimension. But this level right here is all ground. Okay, so that means it's at zero height. And if the voltage is, say, 12 volts, then I'd go up, say, 12 meters, and that would be where this line is. And if you assume the resistance of the wire is negligible, then all of this wire would all be at that same 12-meter height. Okay, so this is 12 meters high, 12 meters, 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 right? Similarly, this wire here, if it's negligible resistance, then it's all going to be 0 meters, 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 right? So by that alone, you can see that this side's 12, and this side's 12, and this side's 0, and this side's 0. So you see that, in fact, the voltages for all of those are the same. And from that, you can say, well, wait a second, the voltages are all the same. So that means V, which is the voltage of the battery, is equal to V1, but it's also equal to V2, meaning the voltage of capacitor 1 is V1, the voltage of capacitor 2 is V2. So what we can do is we can use this and find out what Q is. Q is equal to C times V. So what I'm going to do is I'm going to write C times V, where this is what we call an equivalent. So let's imagine for a second that I'm trying to take this circuit right here and make an identical one that's simpler, meaning it only has one capacitance. What would be the equivalent capacitance that I'd need to represent these two? Well, I'm going to call that C equivalent. And of course, that should be given by C equivalent times the voltage. That should be the total Q that has to go out. Additionally, this would be C1 V1, and this would be C2 V2. But because V1 equals V2 equals V, I can divide through by it. And whatever you do to one side, as long as you do it to the other, is fine. I end up getting C equivalent for for parallel is equal to C1 plus C2 plus ... So I only did 2, but I think you can see that no matter how many you have, the same results would occur. So that's our formula. What that means is by putting capacitors in parallel, you increase the net capacitance. Okay. So for instance, if I had, let's say, this circuit right here, and this one's a 5 microfarad capacitor, and this one right here is a 12 microfarad capacitor, then this circuit would be equivalent to, again, that same voltage battery V, but I could replace this with just a 17 microfarad capacitor, because 17 is what you get when you add 5 and 12. Okay. And it can get more complicated. You know, I can, for instance, say, what about if I do, well, we'll do the more complicated cases when we get to covering the series part. So now let's look at a series circuit. Let's take a same voltage V, say, and this time I'm going to connect it to some capacitors in series. So maybe I'll do 3 this time just to make it look a little fancier. Okay, so this is C1, C2, C3, and I want to know what is the equivalent capacitance for series. I just did for parallel. That's what that's supposed to say there, even though it doesn't look so well. C equivalent parallel. And this is C equivalent series. Okay. Now we got to go through this process again, like I did with that initial circuit, explaining how the charges are going to react. So this battery, again, is going to compel positive charges to stack up over here. And in fact, that's going to get a charge amount of, well, you see the Q is what's going to leave the battery. So it doesn't have any other choice to go anywhere else. So that's going to be a charge Q. But over here, I'm going to get a charge of negative Q. But this was initially isolated, so this part's going to have to become positive Q again. And then this part was originally isolated, so this is going to become negative, and the amount of negative is going to be exactly equal to the amount of positive that comes up here. So again, we're going to get Q there, and then we'll get negative there. So in this case, the voltages aren't the same, but rather the charges are the same. So Q1 is equal to Q2 is equal to Q3 is equal to just plain Q. And what we see is if we wish to actually find the capacitance, we remember C is equal to Q over V. And what I see is as I go from 0 height here, this is 0 meters. Then I'm up to say 12 meters. Then when I get right here, I'm 12 meters, but I drop down by an amount Q over C. So I'm going to drop down from 12 to 12 minus Q over C. And then I'm going to drop down from 12 minus Q over C1 to 12 minus Q over C1 minus Q over C2. And then as I get to here, I'm going to drop down from 12 minus Q over C1 minus Q over C2 to 12 minus Q over C1 minus Q over C2 minus Q over C3. And of course, that's actually going to be 0. So I'm right back where I am. So that tells me that V is equal to V1 plus V2 plus V3. Plus, solving that for voltage, I end up getting V equivalent, or excuse me, C equivalent. All right, is Q over C equivalent is equal to Q1 over C1 plus Q2 over C2 plus Q3 over C3. But as I said, again, these Q's are all equal. So that just gives us that 1 over C equivalent series is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus ... So this is kind of neat. You see that putting them in parallel adds them, whereas these actually makes it such that if you put two capacitors in series, then the total capacitance is going to be less than either one of them. So for instance, let's say I had this battery again, and now I say I have my 5 microfarad capacitor in parallel with my 12 microfarad capacitor. And then back over here, well, this means 1 over C equivalent series is equal to 1 over 5 microfarads plus 1 over 12 microfarads. Ignoring the units for a little bit, we can see that 12, the least common denominator between 12 and 5 is really 60. So I'm going to say this is going to become 12 over 60 microfarads. And this one's going to become 5 over 60 microfarads. And I'm going to get, of course, 17 over 60 microfarads. So ultimately, C equivalent for series in this case is 60 over 17 microfarads. Well, 17 goes into 60 3 times. And of course, then it's left over where we got 3, 3, and 3. It's 9 left over. So that's 9 over 17. microfarads, which I could actually just calculate if I wanted to. So let's do that. 60 divided by 17. Well, I had a bunch of stuff on my calculator already. 60 divided by 17. That's going to give me 3.529 microfarads. So notice the total capacitance of these two was less than even the smallest one. So this type of an equation and this type of an equation are both going to come up, or excuse me, this type of equation are both going to come up quite frequently. It turns out that resistors behave exactly the opposite way. So the formula for resistors in parallel is this one, whereas this one's in series, and the formula for resistors in series is this one. And then not only that, it also turns out that this equation is very much like the lens maker's equation from optics. So it turns out that 1 over the focal length is 1 over the object distance plus 1 over the image distance. So that part alone is another equation that we'll see from time to time. So with this, you can do even more complex examples. You could say, what is the equivalent capacitance of this? So I'm going to imagine a circuit coming here. I'm going to say this is 3 nanofarads. And I'm going to say that's in series with, let's say this is 4 nanofarads, and let's say this is 5 nanofarads, and they're in parallel, in fact, with 6 nanofarads right there. And that's probably good enough. Let's just examine this. So what's the equivalent capacitance? Well, the first thing I want to do is attack this. That's the deepest in. That's the one that's embedded the most. So I'm going to write this and say, all right, I got a 3 nanofarad capacitor here, and I got a 6 nanofarad capacitor here. And I'm going to replace this with just 1. And that's, enough of the drawing. So these two are in series, and series is that crappy stuff. So this is 1 over 4 plus 1 over 5. Obviously, the least common denominator for that is 20. So that'll be 4 plus 5 over 20. That'll be 9/20ths. So I flip that over, that'll be 20 divided by 9. So this is 20 over 9 nanofarads, which would be 2.222 nanofarads, because 9 goes into 22 times. That'd be 18, 2 left over. 2 over 9 is 0.2222. So that works that one out. Now I'm going to say, okay, well, this is the deepest embedded one, part now of these two guys in parallel. So I'm going to make this equivalent to the 3 nanofarad. I keep wanting to write coulombs there. The 3 nanofarad one there, and I'm just going to put it in series with the equivalent capacitance to this. Well, this is 2.222 nanofarads and 6 nanofarads. They're in parallel. In parallel, they just add. So I'm going to say this is 8.222 nanofarads. And now finally, I can replace it with just a single capacitance like this, but 1 over 3 plus 1 over 8.22 is equal to 1 over R equivalent. So in doing that, I'm not going to even try to do it with fractions. I'm just going to go ahead and do 1 divided by 3, add that to parentheses 1 divided by 8.222. Okay, and now I'm going to take that and flip it over. So I got, 0.454955 is what I got for adding these two. Now I'm going to flip them over by raising them to the -1 power. And that gave me R equivalent is equal to 2.198 nanofarads. Okay. So that's kind of a neat little problem you can do, and you'll see a bunch of these. These are sort of supposed to be low-hanging fruit problems. where you just apply a formula. But like I said, there's often, they'll give you hints if it's super complicated, but normally you just start the innermost simplest part. So the simplest part that doesn't have anything to it, it would be this guy, but that literally is nothing you can do with it. So you got to go to this guy, because that's just two of them. And with just those two, you can do something with the series formula. Then you decrease that, and so on and so forth. Any questions on that? All right. So
where does the R equivalent come from? What does that stand for?
Oh, that stands for your instructor being slightly handicapped. That was supposed to be C equivalent.
Okay.
Yeah, I'm mentally ill, evidently, and that's what that's caused. Sorry about that. Oh God, I just can't believe it's. Okay, so let's look at that same sort of circuit, and this time let's put a voltage on there and calculate what the crap happens. Okay, so I'm going to say now I'm going to put an actual voltage on here, and let's say this is 20.0 volts. And that's in fact going to go up here and run into a 3 nanocoulomb, or excuse me, damn, there I go with my coulombs again, a 3 nanofarad capacitor. And then that's going to run into a 4 nanofarad capacitor and a 5 nanofarad capacitor. And that's going to be parallel to a 6 nanofarad capacitor. And this will all come back. So what I'd like to know is the voltages and the charges on everything. So I just said, what are all the voltages and charges? Okay. So what I think about from start is I realize that this is equivalent to a 20.0 volt battery being in series with a 2.198 nanofarad capacitor. Why is that? Well, that's what we just worked out as the equivalent capacitance of all this. Now I have that. That can help me figure out how much charge is going to leave my battery, because I know that C is equal to Q over V. So Q is going to be 2.198 nanofarads times 20.0 volts. And when I do that, I get times 20. I get 43.96, carrying one extra sig fig, say, 96 nanocoulombs. Notice by leaving the prefix in there, I can still say farads times volts gives me coulombs, but since the nano's there, it's going to be nanocoulombs. So that's a wonderful way of dealing with these various units in electronics. You can even combine them where, like, if you divide a mega by a kilo, you get another kilo, stuff like that. So just keep track of what these powers are. That's 10 to the negative 9th, for instance. So now that I got that, I know, in fact, that 43.96 nanocoulombs is leaving the battery. And yes, I wrote that really, really small, so y'all have no chance in heck of seeing it. So that's how much charge is leaving the battery. What that means is all that positive charge has no choice but to go right on here. So I can immediately tell you the charge on this capacitor is going to be 43.96. So Q for the 3 nanofarad is equal to 43.96 nanocoulombs. And then, of course, that can also tell me that V for the 3 nanofarad capacitor is going to be equal to 43.96 nanocoulombs divided by 3 nanofarads. So that gives me 14.65. And that's with one extra sig fig, 19.65. Notice the nanos canceled out with the nanos, so I just get volts. That's pretty incredible. That tells me, remember, if we jump from here, that's the 0 height, and then this is the 20-meter height. That means I've already dropped down from here to 14.65 volts. So it went right here. If I still can put a bubble here, and that really means I'm putting the red terminal of my voltmeter right here, and I'm putting the black over here on the ground. That would read, this is 20.0 volts. And right here, it would read 14.65, or excuse me, 20 minus 14.65. Which is 5.35. So that's pretty neat. It dropped that much with just that one capacitor. I'm gonna try to make this a little clearer so y'all can see it. Okay. Now, what that means is this is also going to compel 43.96 coulombs to go to here. But at this point, it's going to choose a certain number to go that way and a certain number to go that way. Well, what we need is the equivalent capacitance of each of these. Well, this one's easy peasy. But notice also that when I get to the end here, notice this part right here and this part right here and this part right here all have voltages equal to 0 volts. Right? Because they're still in line with the ground side of my battery. So all this is 0 height, 0 height, 0 height, 0 height, 0 height. Now, in reality, the wire actually has some resistance, so maybe it's 0.1. But the main thing is the vast majority of this 5.35 is going across these guys. So I know the voltage on the 6 nanofarad capacitor. So V6 nanofarad is going to be 5.35 volts. Okay. And now that I know that, I can also say that the charge on the 6 nanofarad is going to be equal to, let me box off this so I recognize it's an answer, and box off this so I recognize it's an answer. Now with the 6 nanofarad, all I have to do is take C and multiply it by V, and this is 5.35 times 4. So 5.35 times 4, which should be about 20 something, is 21.4 nanocoulombs. Now, there's a couple ways you could do this. You could find out the equivalent resistance of this and then say, okay, well, I know the voltage is going to be 4.35, and we already did find the equivalent resistance of this. We know that or excuse me, I keep saying resistance. Check me on that, folks. We can find the equivalent capacitance on this. So 4 plus 5, I'll call that the equivalent capacitance of 4 in 5 nanofarads. Okay, we found that earlier by doing the 4 and the 5 one, which gave us 1 over 4 plus 1 over 5. But to get a common denominator, that became 20, and that gave us the 20 over 9, or the 2.22. So now I can say, all right, well, that's just 2.222 nanofarads times 5.35 volts. So 2.222 times 5.35 gives me 11.89. Notice the nano multiplies, so that's nanocoulombs. Okay, now that's a way we could have done it, right? Now, in theory, though, what we know is 43.96 coulombs had to go to this guy and this guy. We just calculated that 21.4 is going to go to this guy. What will we get if we did 43.96 minus 21.4? 43.96 22.96 minus 21.4 should give us 22.56. What did I get for this? This is 1 divided by 4 plus 0.2. And then I say so -1 power. Make sure I got that right. I did get 2.222 as the equivalent capacitance of that. So that was my capacitance. Ooh. I wrote this badly. I was saying this is my capacitance, but then I wrote it right into the formula. Let me change that a little bit for you guys. So what I was doing was recording the fact that the equivalent capacitance of the 4 and 5 nanofarad capacitors was the 2.22 microfarads. So that's all we were doing there. Now that's the equivalent capacitance. What's going to happen is the charge that goes to it is going to build on this side and then cause the exact opposite negative charge on this side, and then that exact opposite positive charge here and exact opposite negative charge here. Those two, in other words, have the same amount of charge. The 4 nanofarad and the 5 nanofarad should have the same amount of charge, and it should be equal to the 43.96 minus what went to the 6. So I want to check again because the numbers aren't looking right. I want to check again and check. This is the 43.96. Let's make sure I did that right. That's 2.198 nanofarads times 20 volts. So that gave me 40. Make sure my math is right. Make sure I typed in everything right. I did. Oh, it's here. I said 2.198, gotcha, times 20. That gave me 43.96. And then, oh yeah. Okay, so that's right. So the 43.96 was right. This 21.4 seems to be right. That's the 5.35 times the 4. So that seems fine. That's the 6 nanofarad capacitor. But when I subtract these two, I suspect I should get that same charge. In other words, 43.96 minus 21.4. And when I do that, 43.96 minus 21.4 gives me 22.56. So conservation of charge says that 43.96 nanocoulombs is equal to Q for the 6 nanofarad capacitor plus Q for the 4 and 5 nanofarad capacitor. Okay, so when I put that in, that gives me Q for the 4 and 5 nanofarad capacitor is equal to 43.96 nanocoulombs minus 21.4. I think that was exactly 21.40. Trying to find where I got the 21. Yeah, it was 21.40 nanocoulombs. And when I subtract those two, I got 22.56. Now that should give me the same answer that I got if I do the other way with here, but for some reason I didn't. So I'm going with this right now just to see what happens, and maybe I'll figure out something that went wrong in a second ago. So both the 4 and 5 nanofarad capacitors are going to have 22.56 nanocoulombs on them. Well, that means those two voltages should add up to give us the 5.35. So let's check that. So V4 nanofarad would equal Q for the 4 nanofarad over C for the 4 nanofarad. Well, Q, we know is supposed to be this 22.56. Again, that's one extra sig fig that I'm carrying in there. And now the C for the 4 nanofarad is supposed to be 4 nanofarads. So the nanofarad, and this was nanocoulombs, the stock guy, sorry about that. The nanos are canceling each other out. So 22.56 divided by 4 gives me 5.64. Whoa, that's too high. What happened? Notice, did I do my math right when I did 20 minus 14.65? 20 minus 14.65 is 5.35. Did I do that right when I did the voltage of the 3 nanofarad capacitor? Well, we said all the 43.96 coulombs have to go to that. And the 43.96 was supposed to be 2.198. Did anybody find any mistakes in my arithmetic that I did here? Because I did part of it with my head. Let's double check that just to see. So here's a way you can actually do this. It's not necessarily the best way, but if I want to do this calculation right here, which is 1/5 plus 1/12, I can do 1 divided by 5. And actually what you can do that, just hit enter and then go plus parentheses 1 divided by 12. And now you've got the 1/5 plus 1/12, and that gives you 0.283 times 10 to the negative third, which is the right-hand side of this. Now I got to flip that over. So I'll say raise it to the -1 power. And that gives, oh, that gives me 3.529. Is that what I had before? Oh, no, it was right. Okay, I did get that one right. So that one checks. The next thing I did was added these two. So 6 plus oh, what did I do here? I did, this is supposed to be equivalent to 3.529, but for some reason I called it 2.222. Where did that 2.222 come from? So there's my problem. That's why I'm getting mixed up figures. So once we got this 3.529, that is not what we used. For some reason we used, oh, never mind. The 5 and the 12 was the equivalent that we used before. So that's fine. Back to this circuit, the 4 and the 5 should have been 1/4 plus 1/5. Let's check that, see if this 2.22 is right. So another way you can do it is I can take parentheses from the beginning and write 1 divided by 4. I think y'all can see that. And then I go outside of parentheses and say 1 divided parentheses 1 divided by, in this case, we were doing 1 and 4 and 1/5. And that gave me the 0.450. Now I got to flip that over by raising it to the -1 power. And that does give me the 2.222. So I'm okay with that. I didn't make that, I didn't make the mistake there anyways. So this is 2.222 nanofarads. I got that part right. Now the next part is these two are in parallel. So I add 6 and 2.22. Which is obviously 8.222. So that checks as well. And now I have an 8 and a 3. So I do parenthesis 1 divided by 8.22222. I'll use as many of those as I can. Plus 1 divided by 3. Plus that's that guy. And now I flip that over by doing invert -1 exponent. And that gave me 2.198 times 10 to the 0. So this part looks right as well. So all that's fine. So you get to revisit that whether you wanted to or not. Now from this, we said this is equivalent, this 20-volt battery is equivalent to 2.198. So I should be able to get the total charge that flows by multiplying C times V. So that 2 times 2.198 times 20 volts gives me 43.96, and it's nano. So I got a nano as a prefix. Farad times volts gives me coulombs. So it's 43.96 nanocoulombs. So I agree with that. Then if I want to calculate the voltage across the 3 nanocoulomb capacitor, then I take 3 nanocoulombs. Voltage is equal to charge divided by coulombs, or divided by the farads, the capacitance. So that's what I was doing there. So 43.96 divided by 3, that gave me 14.65 volts. So that means this side is 20, this side is 20 minus 14.65. And I get 5.35. So this part seems correct. Now at this point, I should be able to calculate the voltage across the 6 nanofarad capacitance. Since this is 5.35, this is also going to be 5.35. And this part right here will also be 5.35. And this part right here should be 0, 0. So yeah, the voltage across that should be 5.35. And when I get 6 nanofarads, and I compare that to find out what the charge is, then the charge for the 6 nanofarad capacitor should be equal to the capacitance Q 6 nanofarads should be equal to 6 nanofarads times the 5.35 volts. Oh, I'm thinking this might be a problem. So multiplying that times 6. 6 times 5.35, oh, it gives me 32.1. That makes more sense. Okay, so evidently when I multiplied, I got the error, and that's right here. So this is no, I don't know what I did to get 21.4. I'm looking back in my calculation to try to find out what I did to get 21.4. So we found the error at least. That's a good thing. Oh, I know. I multiplied this by 4 nanofarads instead of 6. So the actual answer is 32.1 nanocoulombs. Okay, now that we made that correction, everything else should work nicely. So that's how I got this one. Now that's giving me the charge on the 6 nanofarad and the voltage on the 6 nanofarad, the charge and voltage on the 3 nanofarad. So now I just need to find out the charge and voltage for the 4 and 5. And what I was doing was right, except for I was using the wrong number. So there's 2 ways you should be able to do it. Like I said, you can use conservation of charge to figure out what fraction of the charge went, you know, it was 43.96. What fraction of that went to the 4 and 5 microfarad capacitors? And then using that, you know the total charge, and then you just say, okay, well, that charge is going to be shared between both of those. They have the same amount of charge in each of them, in other words, and that amount is what you get when you subtract the 32.1 from the 43.96. So we'll do it the first way, where I won't use that conservation of charge. I'll just use my knowledge of capacitance. So hopefully it'll be clear enough. So now I'm going to say, I know that the Q for the 4 and 5 nanofarad has got to equal 43.96 nanocoulombs, and that's going to be minus the 32.1 nanocoulombs. That is something I know and could be. But what I also know is that the equivalent capacitance of those two, C equivalent for 4 and 5 nanofarads, was the 2.222 nanofarads. So not using this right now, using this, what I'll say is the voltage for the 4 nanofarad capacitor is equal to, notice if you solve C equals Q over V for V, you get V equals Q over C. That gives you that charge over there. Actually, no, I don't want to do that. Oh, yeah. Okay. Yeah. So this is the total capacitance of that whole thing. So I can figure out exactly what charge is going to go there. I was mixing my two ways together and that was bad. So what I know is the voltage across that 4 and 5 nanofarad capacitor is equal to 5.35 volts. That's what we know. If I calculated that right, yeah, 5.35. That was the calculation we just verified. Now I know that has to equal, of course, the charge divided by the capacitance. And the capacitance was 2.222 nanofarads. So I can say that the Q for the 4 and 5 nanofarad is going to be equal to 5.35 volts times 2.222 nanocoulombs. And hopefully that'll come closer to what we expect. So 5.35 times 2.222 gives me 11.89 nanocoulombs. And that's just nanofarads, not nanocoulombs. Stupid me. Okay. Now I can check that. What is 43.96 minus, what is 43.96 minus 32.1? Hopefully it's that number. I'm going to be really upset. Yes, 11.86. Remember, this is one extra sig fig anyway, so I didn't expect it to necessarily get right, but it does round to the right number. So these two check. In other words, they're consistent with each other. So I feel okay about that. So I can now say the charge on the 4 nanofarad is equal to 11.89 nanocoulombs, and the charge on the 5 nanofarad is 11.89 nanocoulombs. So I've got those two now. Now I can also calculate the two voltages, and they better add up to give me 5.35, or else something's wrong with the world, right? So the voltage of the 4 nanofarad capacitor is equal to the 11.89 nanocoulombs divided by 4 nanofarads. So 11.89 divided by 4 is equal to 2.973 volts. And the V for the 5 nanofarads is equal to 11.89 nanocoulombs divided by 5 nanofarads. At least I did it right over there. 1.89 divided by 5 gives me 2.378 volts. And you can see that 2.9 is essentially 3, and 2.3 with 3 gives you about 5.3. So yeah, those are pretty close to each other. And in fact, if I actually add them, I get 5.3505. So yes, they check. So that's a typical type of problem you can be asked to do with capacitors. Obviously, it's not that trivial, but notice how the reducing the individual capacitances to equivalent capacitances actually came in handy and allowed us to figure out some stuff that we couldn't figure out without it. Any questions on that? Maybe I'll rehash and show you exactly what I did to make sure everybody follows. So here's the circuit that we had already worked out. I'd already worked out that this capacitance right here, the 4 microfarad and the 5 nanofarad, excuse me, if the 4 and 5 nanofarad were replaced with a single capacitor, then that capacitor had to be a 2.22 nanofarad capacitor. Then if this whole block was replaced, that would have to be replaced with a 8.22 nanofarad capacitor, because the 2.22 added to 6 gives me 8.222. Okay. And then I found that once I combined that 8.222 microfarad capacitor with this 3 nanofarad capacitor, I said micro again, sorry about that, with this 3 nanofarad capacitor that's in series, then I ultimately got 2.198 for the equivalent capacitance of the whole thing. I used that equivalent capacitance to calculate the total amount of charge that would leave the battery. So solving C equals Q over V for Q, I get Q is equal to C times V. So I took 20 volts and multiplied it by 2.198 nanofarads. That gave me the 43.96 nanocoulombs that's leaving the battery. Now, the way the charge has to behave is it's going to be compelled to move this way, and then it's going to run into this thing with no choice. So all of that charge is going to be pressured onto this first plate. So that'd be positive 43.96 nanocoulombs on the left, and then a negative 43.96 nanocoulombs on the right. That's going to then cause a positive 43.96 coulombs to go into this junction, this part where one wire breaks into two, and some fraction of them is going this way and some other fraction is going to go that way. And we got to figure that out. But first I wanted to go ahead and figure out, well, now that I know the charge on that first capacitor is 43.96, what is the voltage? Because if I knew the voltage, then since this one's in parallel with these two, I can tell the total voltage across that. So what I did was calculate the voltage of the 3 nanofarad capacitor using V equals Q over C. So I took the 43.96 nanocoulombs divided by the 3 nanofarads and got 14.65 volts. Okay. Now, when I take that and realize this, just like a resistor, would have to be a voltage drop, because obviously the highest point of the voltage should be right next to the battery, and therefore right next to the capacitor, then I took 20 minus 14.65 and got what the voltage should be on the other side, which is 5.35 volts. So I know the voltage here is 5.35, but that also tells me that the voltage here on this side of that capacitor and on this side of that capacitor is 5.35. And since the ground side of the battery would be 0, then that means this part's 0. So that means a whole 5.35 volts is across the 6 nanofarad capacitor. Now I can use that 5.35 volts to find out the charge on the 6 nanofarad capacitor. And charge, of course, is given by capacitance times voltage. So I took the 6 nanofarad capacitor and capacitance and multiplied that by 5.35 volts and got 32.1 nanocoulombs. Some reason I made a mistake earlier, but now you see why I got the 32.1 nanocoulombs. Now, in principle, this figure, if I subtracted 32.1 from 43.96, that should be the total amount of charge that goes to all those. And that's about 11.86. Again, I'm carrying one extra sig fig, so it's 11.9 really. But I chose not to use that. I chose to use instead the fact that the equivalent of these two capacitors was 2.22. And since whatever charge goes to this one is going to be the exact same charge on that one, therefore, I can calculate the charge on both of them just by treating the equivalent capacitance. So the equivalent capacitance was 2.22. The voltage had to be 5.35 across the equivalent of the two. So the actual charge would become basically found by taking the 5.35 volts and multiplying it by the capacitance, which is 2.22. So this times this gave me the 11.89, which is essentially 11.9 nanocoulombs. So I know that's the amount of charge that's going on arm of the circuit. Therefore, 11.9 nanocoulombs positive will be here, negative will be here, positive will be there, negative will be there. So the two charges on those things are supposed to be identical. And in fact, that is close enough agreement with conservation of charge there. So now all I have to do is calculate the voltages on each of them. And of course, voltage is given by charge divided by capacitance. The charges were the same. So I did 11.89 divided by 4 nanofarads and got 2.973. And then I did 11.89 divided by 5 nanofarads. And of course, that gave me, since this was, that unit's not good. That's supposed to be 11.89 nanocoulombs. Okay. When I divided that, I got 2.379. And lo and behold, if I add V4 in F plus V5 in F, I got 5.3505 volts, which is another good check, because we had already said that it's in parallel with the 6 nanofarad capacitor, and we said that voltage was 5.35. So that's the kind of stuff you should be checking every time you do these problems, is looking for that. Luckily, I mean, that didn't necessarily pan out itself to make this instruction very easy, but that's what kept me from, made me stop the problem when I didn't get conservation of charge here. I knew something was wrong, and luckily was able to find this 32. So if you take the time to check at each point, hey, is conservation of charge acting? Hey, is the voltages add up to give you the total voltage? That sort of thing. If you do that, that'll keep you from making some of the more careless mistakes, or more, mathematical mistakes. So any questions on that? Okay, so here's another type of example. Let's say, where's my black thing? Oh, there it is. I don't know. Well, yeah, I'll say this. Okay, let's say we take a, let's say 10. Oh, this pen's dying too. Good Lord. Oh, my pens are dying. Let's say we have a 10 nanofarad capacitor in parallel with a 20 nanofarad capacitor. And let's put that on a circuit with, let's say, 100 volts. Okay. So what I'd like to do is I'd like to find out what is Q1 and Q2. Okay. So they're in parallel. So that tells us something already. We know they both have the same voltage, in other words. So they both have the same voltage, and that voltage is 100 volts. So V1, I guess this pin's still not going to write. Just because I switched hands doesn't make it right. Well, maybe it will now. V1 is equal to V2 is equal to V battery, because they're in parallel, which equals 100 volts. Okay. Q1 is equal to, from C equals Q over V, is equal to C1 times V1. So I'm going to say that's 10 nanofarads times 100 volts. So this is in fact going to give me 1000 nanocoulombs, but a nanocoulomb is 10 to the negative 9th, so I can say that's just 1 microcoulomb. Okay. Now, what do you think is going to happen? This other one's twice as big a capacitor. Do you think it's going to hold even more charge or even less charge? This is the sort of thing where I told you about never solve a physics problem whose answer you don't already know. We just want you to take a guess at it so that you can correct your physics logic. So we've got 2 capacitors in parallel. Which one wins the largest charge? The bigger capacitor or the smaller capacitor? Can anybody think? Well, check out this. If you take C equals Q over V and you solve for V, You see V is equal to Q over C, and that means Q1 over C1 is equal to Q2 over C2. So if this number is big and this number is small, then this number is going to have to be bigger to account for this number being so small. My daughter's calling me. I'll have to put that. So you might think that the bigger capacitance will have the bigger charge. So now let's check our logic with that. Let's see if it actually worked out. So what I'm going to do is I'll say Q2 is equal to 20 nanofarads times 1,000 volts, or excuse me, times 100 volts. So that gives me, in fact, 2,000 nanocoulombs, which is 2 microcoulombs. So yeah, the bigger capacitor did in fact get the biggest charge. So we can now remember that when circuits are in, or when capacitors are in parallel, the largest capacitance leg will get the majority of the charge. That turns out to be the same thing that happens with the current for a resistor, except it's reverse on that. When we do a resistor in parallel, the lowest resistance is going to get the largest current. And that's because the formulas are just opposite for series and parallel with capacitors versus resistors. So there's our one result, and there's our other result. So that's a nice, neat little problem, and it gives us a chance to make some sense of how the physics should work. And obviously the physics works such that the bigger capacitor gets the lion's share of the charge. Now let's do something. We've got some time. I'm going to take that same scenario, and I'm going to take that 10 nanocoulomb capacitor, nanofarad capacitor, sorry, with 1 microcoulomb on it. And this will be the positive side, and this will be the negative side. And then I'm going to do the same thing, but I'm going to flip the other capacitor. So this will be the positive side, and this will be the negative side. And this is the 20 nanofarad capacitor, and this has 2 microcoulombs on it. And then I'm going to connect them. Okay. In other words, I'm putting the positive to the negative and the negative to the positive. And what I want to figure out now is what is Q for the 10 nanofarad and what is V for the 10 nanofarad and what is Q for the 20 nanofarad and what is V for the 20 nanofarad. Okay. Well, now that I've got them like that, what we find out is, of course, the Q10 minus the Q20 is going to be equal to the total. So what's going to happen here is the the 1 microcoulomb and the 2 microcoulombs are going to come compare to each other, and they're going to sort of, basically equilibrate out so that you get the sum of those two, Q10 plus Q20. So that's sort of our problem. And not only that, we're going to look at it and say, well, when I do that, what actually happens to the voltage? Well, the voltage is now going to be, this is the original, by the way. The voltages are now going to be the same, because what's going to happen is they're now in parallel, so they'll be the same voltages. So what I want to find is these are the original charges, which was the 10 farads and the 20 nanofarads. And what I want to do is I want to find out what the new charges, say Q1 and Q2 would be, or Q10 and Q20 would be. Actually, I said that backwards. Hold on. Let me use a better symbol, because this is getting ugly. So we'll call the capital Q's. We'll call those the charges that they got after I charged it up. So those are capital Qs. And what I'm going to say is when they're connected like this, they're going to have new charges on them. And let's call this one, this is a 10 nanofarad. Let's call this one the Q 10. And let's call this 20 nanofarad. And let's call this the Q20. Okay. So the reason why I do that is I know I have 10 nanofarads positive over here and 20 nanofarads positive over here, but this positive 20 nanofarads is going to cancel, or excuse me, this positive 2 microcoulombs is going to cancel out half of those. Well, I shouldn't say half of this is going to cancel out half of those. That's the easier way of saying it, because the positive with the negatives are going to just cancel each other out to get 0, and I'll still have 1 microcoulomb left. So what I would say is Q20 minus Q10, which is what we had up here, and this I've called now should be the Q10, and this should be the little Q20. So those two should basically subtract to give you the sum of the two. So Q1 plus, or Q10 plus Q20. So Q20 minus Q10, that's 2 microfarads minus 1 microfarad. So I get 1 microfarad is equal to Q10 plus Q20. That's all the charge I got to work with, right? But I also know that the voltages have to be the same. Specifically, Q1 or Q10 has to equal C10 times V. And the V is not going to be the 100 volts that we had earlier, by the way. It's going to be something else. But we also know that the Q20 is going to be the C20 times the V. So I'll just call this V. Well, I didn't really call it V before, so we'll just call it V and leave that as a symbol. Okay. Now, the point of it is that this new voltage should in fact be the exact same for both of them. So I get that Q10 over C10 is equal to Q20 over C20. So now I've got two unknowns. Actually, I had three. The new voltage was another one, but I have three equations, this one, and this one. What I just did was eliminate the voltage as an unknown by setting these equal to each other. So now I have two equations and two unknowns, and all I have to do to get one is substitute what I know. So I'm going to say now that 1 microfarad is equal to, well, Q10 is going to be equal to C10 over C20 times Q20, and then plus Q20. See what I did? This tells me that Q10 is equal to C10 over C20 times Q20. So if I plug that in for this one right here, I get that. But we know this is in fact just 1/2 because that's what 10 microfarads or nanofarads over 20 nanofarads. So it's just 1/2. So I get from this, I get 1 microfarad is equal to 1/2 Q20 plus Q20, or further still, I can say 1 microfarad is equal to, and by the way, the units have now changed. So by dividing by the, oh, that was supposed to be coulombs. Now I know why. I was sitting there saying, wow, I got farads over there. Yeah, I was supposed to write the charge there, not the farads. Anyways, back to this. I got 1 nanocoulomb, 1 microcoulomb is equal to 1/2 Q20 plus Q20. Well, 1/2 plus 1 is 3/2. So that's 3/2 Q20. So I can now say that Q20 is in fact equal to 2/3 of a farad, or 0.666 micro. And I said farad again. Damn it! Well, I keep writing farads for capacitance and capacitance for coulombs and everything else. So it should be 0.666 microcoulombs. Now we have that. We now can say, well, Q10 is supposed to be equal to 1/2 of Q20. So Q10 should be 1/2 of 0.666 microcoulombs. So this one's going to be 0.333 microcoulombs. So I now have the two new charges, and all I have left is the voltage. And to find the voltage, of course, voltage is just equal to Q over C. So I can do Q20 over C20 if I want. And Q20, of course, is 0.666, 0.666 microcoulombs over 20 nanofarads. 0.666 divided by 20. That gives me let's say 0. The calculator gave it to me in a weird format. I'm going to say 0.0333. That should come out micro over nano, should be kilo. 10 to the -6 over 10 to the -9 should be 10 to the +9 minus 10 to the -6. Yeah, that should be kilovolts. Okay, so that of course doesn't make much sense, but it's going to be 33.3 volts. So by disconnecting them that way, we actually did find the ultimate voltage, and the ultimate voltage is about 1/3 of what it was when we left them, when we charged them up initially. So since that problem was a little complex, a little convoluted, I want to go over it again, just express to you what we did. So initially we had the problem where I took the 10 nanofarad capacitor and put it in parallel with a 20 nanofarad capacitor. And then we just calculated what the charges would be if I connect it to a 100-volt power supply. So this 100-volt battery sent the same amount of charge to each of those, or excuse me, the same amount of charge, well, I shouldn't say so, set up the same amount of voltage for each of those. So both of those had a voltage of 100 volts, but because one has a higher capacitance than the other, we expected some dissimilarity between the charges, because obviously capacitance relates charge to voltage, and both of these have the same voltage. So they can't have both the same charge and voltage if they're different in capacitances. So setting that equal to 100 volt, we can just say 10 nanofarads times 100 volts gives me 1,000 nanocoulombs, which is a microcoulomb. And then 20 nanofarads times 100 volts gives me 2,000 nanocoulombs, which is 2 microcoulombs. So that was the total amount of charge that we had on these. We connected them disconnected them very carefully, and then we took them and reconnected them backwards. And conservation of charge dictated that I couldn't just destroy any charge. So what happened was the +2 microcoulombs canceled out one of the one of the microcoulombs and left another +1 microcoulomb. That had to distribute itself over in such a way that the Q10 plus the Q20 was equal to that 1 microcoulomb. So that's why I set Q10 plus Q20 equal to 1 microcoulomb. Now, the fact that they are now in parallel tells you that had to be the same voltage, but that voltage is not necessarily the same because the charges have been redistributed. So what I had to do was set up the fact that the voltages were the same. And that was established by saying, well, the Q for the 10 would be the capacitance of the 10 times the voltage, and the Q for the 20 would be the capacitance of the 20 times that same voltage. So solving both of these expressions for V and setting them equal to each other, I was able to eliminate the V. And then by solving for Q10, I was able to eliminate the Q10 and plug it in this original equation. So with that, I got that 3/2 of Q10 was equal to I don't know why I wrote it that way, but 3/2 of Q20, excuse me, was equal to 1 microcoulomb. So that 3/2 allowed me to solve for Q20, and that became 2/3 of a microcoulomb, which is 0.666. Then I could go back and use the same result, which is basically multiplying by 1/2 to tell us that Q10 was going to be 0.333. Again, we got the smaller capacitance with the smaller charge held up. And finally, I could calculate the voltage by taking the Q20 over C20, or I could have taken the Q10 over C10, and this should have been a lowercase q. Either one should have given me the same answer and would have given me the same answer. So I took the Q20 over C20 and got 33.3 volts. So that's the new voltage. Yeah, that's kind of one of the most tricky problems to solve of this variety. But once you get the idea that realizing that these two are in parallel, and two, that charge is conserved, so you can get this equation right here and get this equation right here, then it's not too hard. So I would try making up a similar problem and see if you can solve that as well without looking back at your notes. If you get stuck, look back in the book does a problem just like this. You can look at that, or you can look back at this video or whatever. But anyways, at least look at the end part where I made a synopsis of what I did. That'll be a lot cleaner, as often happens with the problems. So it's now 6:08. You guys are supposed to get out at 6:05, so I guess you're free to go. If anybody has any questions, I'll wait around. And thanks for coming, everybody.
Have a good night, Professor.
You too. Man, that was a bad time. James, do you have a question? All right, well, I'm going to go ahead and split. Have a good one.